Welcome back. You have seen us do all sorts of welding on this channel, from arc welding to MIG welding to TIG welding to diffusion bonding, otherwise known as forge welding. Well, today we're going to learn about something new. Friction welding. We're outside Cambridge at the Welding Institute, and since 1946, this place has existed to research, refine, develop, and test welding processes, and have been at the forefront of innovation in welding technology since. We're going to see 3 different processes today: rotary friction welding, linear friction welding, and friction stir welding, which is even developed right here. Let's jump in. Kate, thank you so much for having us today.
Welcome to the friction welding section at TWR.
Brilliant. So we've got 3 machines to look at. Why do we even entertain the idea of friction welding? Like, what's the background to us needing friction welding in the world? Why?
So friction welding is a solid state process. So we don't melt the material while we're welding. It's not really even welding at all. It's a complete lie. And actually that means that we get much better properties within the weld because we've not got that melting process. So things haven't kind of melted and re-solidified, so we don't get cracking within the weld, we don't get pores within the weld, we get much better weld quality. We also are working at a much lower temperature, so we don't get as much distortion in the weld as we would do if we were using a fusion welding process.
So this means that you've got all sorts of capabilities or possibilities from that you wouldn't otherwise have.
Yeah, and we're able to therefore join dissimilar materials as well, a lot easier than other processes, and we're not adding an extra alloy in by using like a filler wire. So we don't add anything into the process, we just use.
So we're not going to see any filler wire today?
Not today.
We're not going to see any molten metal?
No.
Am I right in thinking that this is effectively diffusion bonding that's happening? It's just that you're creating the heat in a different way?
You're both creating the heat through friction, but also you're using the tool or the parts themselves to stir the material together.
So we're going to look at rotary friction welding. What would be the use case of rotary friction welding, and why wouldn't you just MIG weld the thing together?
The use case of rotary friction welding, for instance, what I did my PhD on, aerospace discs. So within an aerospace engine, you're joining nickel superalloys. Those are really, really high temperature materials, and they're really hard, like physically hard. When you weld them, it's just super challenging, just even to get a weld ore that would be at a good enough level, a good enough quality to put into an aerospace engine. So by rotary friction welding them, you get much better quality on the weld, and you're able to keep those properties really high and use it at that level.
So it's for cylindrical components.
Cylindrical components, yeah.
And it really comes into its own on alloys that are very challenging to weld through other means.
Yeah.
All right, let's begin. Rotary friction welding.
So these are some of our rotary friction welding samples.
So stainless, mild steel, aluminium, copper, stainless, titanium. Oh, you're doing a stainless to titanium with an aluminium interlayer?
Yeah, so even with friction welding, stainless is pretty hard to join to titanium.
And I presume that aluminium interlayer is rotary friction welded onto one part, machined down, and then rotary friction welded together as the interlayer.
Exactly like that, yeah.
Wow. Ollie, pleasure to meet you.
Nice to meet you.
You're going to be showing us around your rotary friction welding machines, eh?
I've got a small demonstration set up, so let's go and have a look.
Brilliant. All right, so what do we got here?
So we've got a small benchtop machine set up, pneumatic control system, capable of welding 10mm and 13mm diameter bar.
Great.
So we've got a 10mm bar set up today. We're going to be doing a steel weld.
Brilliant. And then you've got a bigger machine here.
Got a bigger machine here, yeah, capable of doing 50 up to 80mm diameter.
So that's basically a lathe with an hydraulic press attached to the end of it. So this will do bits of round bar like this, and this will do bits of round bar.
Bits of round bar like this.
Like that.
Quite a comparison.
What's happening in rotary friction welding? What's happening to the metal?
Well, there's a process happens where there's a light touchdown when the material touches, then the friction force is applied, and then that generates the heat, and then as it pushes, it forges and rolls the material out, and that's how the process works. So the process there's no melting occurs, it's fully solid.
I get to press the button.
Yeah, that's the whole reason you're here, Alec.
Oh, thankfully, it's very nicely labeled. All right, welding. Wowza! That is quick. Look at how much material has been like upset to the outside. That is very cool. You can see how oxidized the bits that were hot are, but inside the weld, that's not oxidized.
All the oxidants and contaminants get pushed out through the friction, so that comes out, so that rolled material is what we call the flash.
So there's no way for oxygen to get in there. So you can do crazy materials like titanium without needing to be in an inert atmosphere.
Yeah.
That is cool. And the strength of that weld, is it kind of comparable to the raw material?
Well, we've done a project before. We've welded 4mm steel bar, and it went through a lot of fatigue cycles. We were able to bend it 105 degrees without it snapping.
Oh, wow.
So, very strong stuff.
Should we do a few more?
Yeah, let's do it.
What are you doing over here? Oh, you're gonna release it by moving that hole. Okay.
And there's your first rotary friction weld.
That is really quite beautiful. Those things are now stuck together forever. Round 2. I'm very interested in how those parts shorten as it's welded, because there's a lot of upset flash. There is a certain amount of material that gets out of the weld area. So these parts are 51mm, means 2 of them is 102. Now we load it. Now we got it out, and now it's 96.5. That lost 5.3mm. Interesting. It's not lost, it's just, it pushed it out of the way. What is the craziest combination of metals that you've bonded in rotary friction welding?
So we've got a project on at the moment. It's welding plastic. So we're actually welding PPS plastic to GRE fiberglass.
Oh, wow.
Which is pretty cool.
Plastics too? This has got me very tempted to try and do some rotary friction welding here in the workshop, but it's also got me working up a thirst. That is delightful, and I'm so thrilled that Element is today's sponsor. It's a zero-sugar electrolyte drink that keeps me hydrated when I am here in the workshop, and I love it for a sweaty day in the workshop, so much so that I've always got to have it in reach. Each sachet's got 1,000 milligrams of sodium, 200 milligrams of potassium, 60 milligrams of magnesium, and I don't just love it when I'm in the workshop, I love it when I'm up in the mountains, working hard, getting a sweat on no matter the season. And the best thing is, just for you, if you go to the link in the description and you use code FORGE checkout, with every purchase of Element, you're gonna get a free sample pack. So go get 1 or all 3 of my favorite flavors. You'll get 8 sticks thrown in free at drinklmnt.com/forge using code FORGE at checkout. Thank you, Element, for keeping us hydrated. Let's get back to TWI. So if we need a round part to join it together, we can use rotary friction welding. What if you just want to join 2 flat bits of metal together that you can't necessarily spin?
Oh, we can use linear friction welding.
Let's go learn about linear friction welding. Ollie, thank you so much for your time. Pedro, pleasure to meet you.
Nice to meet you, Alec.
I would like to learn about all the things that you find interesting and exciting about linear friction welding.
One of the things I find really interesting about linear friction welding is that it's a process that has been around since the 60s, 70s. It's been used in multiple applications because it's derived from the same principles of rotary friction welding, but allows you to better join, profile, or prismatic components. And this enables you to do a wide range of products in specifically for the aerospace sector, where you have such a need for high quality joints. In a nutshell, if you have never seen a linear friction welding, basically it differs from rotary friction welding in the fact that the components oscillate up and down in a sinusoidal motion, the same way we warm our hands in winter when we want to, when we're feeling cold.
Same principle.
Literally. Same principle, joins metals, natural materials like wood, ceramics.
You can do it with wood.
We can do linear friction welding of wood.
Oh my goodness.
So it's a pretty versatile process.
And so it's all the same as the rotary friction welding in the sense that it is movement and then a hydraulic press applying a certain amount of force. The movement generates the heat, the hydraulic press squeezes them together, it stirs, creating a solid state bond.
Exactly. One of the main things that I like about friction welding is that what some people would describe as bulk additive manufacturing, in the sense that you can create complex shapes from a near net shape. This is a good example, for instance. This is a part where you have this intricate design, you have this tab here, you have this part on the back. If you were to machine this from a solid block, you'd have to start with something that's at least this wide, this long, and this tall. So can you imagine the amount of material that you'd have to remove layer by layer, step by step?
It would be effectively 60-70% removal?
At least, yes.
All turned to chips?
All turned to chips. How did linear friction welding enabled savings on this? Instead of getting all of that material, you have a linear friction welding here, another linear friction weld there, another linear friction welding there, and you have a much thinner piece of material, which basically just covers you for machining tolerances and you reduce the amount of your machining and wasted material as well.
Wow.
Another example of big chunks in one go, for instance, is this one for a pylon bracket, where this block being welded to this block, this assembly then welded to this block, which then is welded to this block.
Oh my goodness. This is another crazy example, right? Imagine that would be a 9-inch block of titanium
Yes.
to machine this from,
Yeah.
but you can add these components?
Titanium forgings are extremely difficult to procure, but even forging, you'd come up with, because forgings tend to come in very non-optimized sizes,
Yeah.
so you'd still have a lot of machining from solid,
Absolutely.
which you can recycle some of the chips, but it's just so much time consuming when you can work on something that is nearer to net shape, which was a concept of this one. But the other challenge of this particular part is the tightness of all of these welds. It's a process that inherently involves stiff clamping systems, because there's a lot of force and there's a lot of motion and momentum that goes into these parts.
So if you need to hold this dead rigid,
Yeah.
and you only have that space to build a fixture, that's really challenging.
To that point again, if you have sufficient force on your hydraulic ram, there's nothing stopping you from doing 2 welds at a time.
Okay, so that means on a part like this thing here,
That's exactly how that was done.
and those 2 weld surfaces can be done at the same time.
This part and this part, these are example of 2 welds in one weld
Okay,
cycle.
so you're welding all these 3 components in one weld cycle.
Yeah, so
in
this
order to-
is the aftermath post machining.
Yeah.
But effectively, these are 2 chevrons that were welded at the same time, instead of one at a time.
That is amazing. I am inside the linear friction welder, and what you'll see behind me is an enormous hydraulic power pack. That pumps oil into these accumulator tanks, where the nitrogen compresses, meaning that it can be pumped at an incredibly high pressure and flow rate to a cylinder here to actuate the oscillations. This head is going to go up and down on our piece 2 millimeters and 50 times a second, vibrating. These hydraulic hoses are what is providing the hydraulic pressure to clamp the part. While on this side, a hydraulic cylinder with load cell attached is pushing this ram, forcing this side of the workpiece against that side of the workpiece with 7.5 tons of pressure for this example. As it oscillates, it'll heat up, get forged together, and when it stops, it'll be one piece. Imagine you put a 7.5 ton weight on these 2 bits of metal, and then you're asked to slip one back and forth 50 times a second. Let's see if we can see it run. That was pretty quick.
That was pretty quick.
It's stuck together. Yeah, that literally took 3 seconds.
Yeah, it is a very, very fast process, but people sometimes underestimate quite how fast.
No, I imagined more happening from the machine, but yeah, it's only a 2 millimeter oscillation, so it makes sense. How large of a surface area can this machine that you've got here join?
So we're relatively limited on the size we can use on this machine. In terms of physical capability of linear friction welding, there's no limit. As long as you can hold it and you can apply that pressure and you can oscillate the part, then you can weld it. But obviously, the size of the machine tends to limit the size of the components that you can do. This is quite small for a linear friction
I imagine you can get
Some
them
of-
big enough to fill up the room.
Some of them are as big as a room, yeah. So another interesting thing is that when we're running these welds, we actually capture all of the forces and the oscillation as we're doing it.
Oh, wow. So you got all the data. So you send this to your clients and they can then do something from it.
Yeah, so they can use that data. They'll also use that data in production, so they'll make sure that their process is within certain limits. If it's outside those limits, they'll know, okay, it's not welded to our production standard, and they'll be able to throw that one away out of the batch.
Let's see some more. Gosh, that's cool. Industry obviously requires things a little bit more complicated than 2 small flat coupons. If you're the European Space Agency and you need this part made from components like this, the fixturing to hold them in that linear friction welding is super critical. Look at that beautiful tooling. Well, it is designed and made in-house by Stuart. Stuart, it's a pleasure to meet you.
Morning.
So as I understand, the challenge that you solve here is holding complex parts.
That's right. Because we're doing friction and forge, there's a lot of forces involved. It's not like a MIG weld where there's no real force on it, you're putting the heat into it. We actually generate the heat by actually the friction that we cause, and because of that, we need to hold the component really tight.
You eventually come up with this, but what's the beginning? You go to your work area.
We do,
And
yes.
you design it.
We do.
What are kind of some of the first stages that you think about when you're trying to design this? Are you going pen and paper?
Yeah, we go pen and paper first. Generally, you can do a lot of number crunching, and ideas can come and go quite cheaply. If you can imagine, it's expensive to start drawing stuff and then find out you've got a problem and then have to go back down that ladder and start climbing again, whereas the best thing to do is to get a few people in, get an idea, and then introduce the other people to it so that you've not got too many, because you can have too many people sometimes.
Yes.
Once you've then got that, you can then move forward with the design. The tooling that was outside, here we have the CAD model that would have been created for it. So what we actually do is we draw each component, and we can do some number crunching and make sure everything fits. And then we move on to the CAM, and we import the files from the CAD directly.
So now we're looking at the CAM file for the fixture in the linear friction welding machine. This isn't the CAM file for cutting the components in the milling machine. This is the CAM for the linear friction machine.
That is.
Because that's very important to make sure that everything is going to fit and locate.
Yep. So you can see the bed of the actual linear friction machine, because heights are very important. Obviously, we need that when the component stops and freezes the weld, we want it to be aligned. And if we don't have that dimension machined into the tooling, then when we stop, we could be out of position. So we have to be really close on what we produce.
Okay.
I'm used to looking at things like this, and you can go right the way in and zoom, and you can see the actual component sitting inside. You might just see it sitting above surface.
Yes.
Yeah, because when we put the cap on, we actually want the bolt down force to go into the component and not sit on the top of the jig. Hence the reason why the pink is sitting just.
So you have a little bit of clearance to make sure that you're actually applying pressure on the part.
But generally, that's the main assembly. Then you can bring out your separate components.
Okay, and so we're now looking at that component more on the manufacturing side
Yes.
of actually machining this in your milling machine.
Correct. Generally, then what you can do is you create different machining aspects to produce the component. Once you've done that, you can then run a test.
So you can scrub through all the tool paths.
Yep. Then if you just hit the button down there, it produces the G code that you then run in the machine.
So all of these numbers get exported to this milling machine to make your fixtures. I think that working in an R&D machine shop must just be fantastic. How long have you been doing this?
38 years.
R&D machining for 38 years. I'm sure you've seen a lot of changes in that time.
Oh yeah, definitely.
Wow.
I used to program by hand, and then I moved on to CAM and doing it with the drawings, which is much easier.
That is incredible. All right, this mill, what is it?
This is a Colchester milling machine we've just recently purchased.
It's a Colchester.
Yes.
A British CNC mill.
It is.
My first ever lathe was a Colchester student lathe. This is a Colchester CNC mill. I didn't know they did them. I presume you've got a tool changer.
Yep, 22 tools.
22 tools. If somebody is interested in doing what you're doing, R&D machining, how do you end up in your position? What would you say to a young person that is interested? What would they need to do?
Be interested in engineering, yeah, and how things work, and how you're going to, in some ways, break the rules. And you can find that you've got a new idea that you can try out instantly rather than having to buy something off a shop shelf. You can actually come here and produce something which in some ways may never have been made before.
I can tell that you love what you do.
Yep.
Brilliant. Well, thank you so much for showing
No
us your
problem.
workstation.
That's cool.
Really honoured. Rotary friction welding led to linear friction welding. And in 1991, right here in Cambridge, friction stir welding was developed. And I know absolutely nothing about it. Hello, Nathan.
Hello, how are you?
I'm doing great. Thank you
Hi.
so much
Nice
for
to meet you.
teaching us about friction stir welding.
Yeah.
It was invented right here in 91?
In 91, yeah. I came in 97, so I've been friction stir welding for the last about 29 years, I would say.
Okay.
Yeah.
So you're pretty new to the job?
Yeah, pretty new, pretty new.
Okay, but I'm sure you'll be able to give us the rundown anyway.
Yeah, certainly. Should we go and have a look?
I'd love to. Thank you so
Okay.
much. Gosh, This thing is monstrous.
So what we've got here is a gantry-based friction stir welding machine. Now this was built on a European project. So this was built to industrialise the process. It has got two beams. So this first beam is 11.5 tonnes. The second beam over there is 12.5 tonnes. And the reason why they're so well built and strong is to stop deflection. When we plunge our tool and rotate and plunge the tool into the workpiece, we don't want to push back the machine.
This is a monstrous bit of equipment, that is for sure.
So we've got different working tables. So we've got low tables, so we could put jigs and fixtures on
Oh
this
wow,
table.
so you could
Yeah,
build an enormous fixture on that.
Be able to do a tank or something like that on here. And we have different locations. So we've got a vacuum bed over there, and this bed we'll be using over here.
Wow.
So we're going to be welding pure copper
We're going to be welding these 2 sheets of 8mm copper.
together.
Brilliant.
One pass.
In one pass.
One pass. We pop our bits in. So with friction welding, we always have to clamp material very tightly to stop it moving around. Because if we start having parts that move around, we're not creating any friction or heat.
You don't have any gap on the bottom, it's going straight on the steel.
Yeah.
So you're going to get a full penetration weld, even though it's straight backed onto steel.
Straight back onto the steel.
What?
Yeah, that's
Oh,
good.
yeah. I don't think it's going anywhere.
So this is the tool we're going to use. This is a tungsten-based tool. Heat of the copper when we weld it is about 700 degrees C. So it's got to resist.
Is that
700
above
degrees.
the melting temperature or below the melting temperature
Well,
of copper?
we don't actually melt. We plasticize, and we make a very, very low temperature weld, which keeps the properties of the plate intact.
So just like the other processes where there is no molten metal, in rotary or linear friction welding, in friction stir welding, it is saying solid state.
Solid state, but plasticized.
How is that tool going to plasticize that and stick that together?
You're going to find out.
It looks like a backwards end mill.
It creates frictional heat and then stirs both sides of the plate together.
You're going to run the tool through the seam, the interface between both plates.
Yes, yeah.
That tool's going to be spinning, and the tool is going to be rubbing on the material, heating it up. In that hot state, it's plastic enough that it's then going to be just throwing it all over the place, stirring it together.
Stir it together. And the shoulder is there to encapsulate the weld afterwards.
So it doesn't just fly everywhere.
Fly everywhere. You might notice that we've got a slight tilt on the head.
They've got a little lean over there, right?
Yeah, a little lean. And that gives us a forging action on the back end of the shoulder. It irons basically the weld when it's finished.
Wow.
So we just check our welding parameters. So we're going to plunge. We need to plunge at a rate of 20 millimeters a minute and a rotation speed of 250 into a set position, and it will dwell there to get heat into the tool and into the plate. And then we're making a weld of 230 millimeters long and a traverse rate of 120.
250 RPM. Not very fast.
We don't want to make it too hot, because if we make it too hot, we'll lose the properties of our material. So we're in our set position, coming down to our reference point.
There's the seam.
Now we have a little start hole there. So it's just to relieve the material to make sure that we get this shoulder down to the top of the material.
And that hole doesn't go the whole way through.
Right, we ready to go?
I'm ready. Okay, so this is that slow down feed you were talking about,
Yeah.
the 20 millimeters a minute. And now the shoulder is rubbing on it.
Yeah. And we've got a set force of 45.
So it's going to be putting 4.5 tons of downwards pressure on the surface of the piece.
Now we're getting some heat into the material there.
And the hole has
See the-
disappeared.
Yeah. The
hole
hole
is
is
gone.
traversing along the joint line.
What?
Tool.
Oh, the hole is just moving.
Yeah.
Because the tool is filling in behind the hole as it goes forward.
Is that links?
Is it taking material from in front of the tool and pushing it to the back?
Yeah, it's finding its way round all the time.
So material that was in front of the hole got pushed back around and filled in the back of the hole.
Yes. And then you've got your forging action of the shoulder, moving
That's-
the material down.
Unbelievable.
As you can see, it's not that hot.
There's no filler material.
No filler material, no gas. It's very safe. So
We're away from the machine.
We're away from the machine.
There's no smoke.
No smoke.
There's no dust. It's quiet. There's no screeching. That's cool.
There we are.
We're at the end. Look at that. You can see how the heat builds up over the course of the cut. How there's almost no oxide to it, then there's a little bit more oxide as it's got hotter as it goes, but I mean, that is not very hot.
Right, should we take it out?
Yes, please.
And there we go.
That is nuts. It's not gonna drop apart on us.
No, no.
What?
There we go.
How did you do that?
Subscribe to Alec Steele.
That is outstanding. How did you put that in there? Is that on the...
That's on the backing bar.
How did I not spot that? A treat. So the bottom of that tool is just ever so slightly up from the bottom of it.
Yep.
It's still getting hot and it's still getting plasticized and stirring, even though the tool isn't all the way through.
And yeah, as you can see, this is a low distortion process because these plates have not distorted.
Yeah, there's no chance you're going to weld two bits of plate together like that with a MIG welder and have them stay flat like that. Wow. And if you bend this thing, will the friction stir weld break in the weld or will it break elsewhere?
It will break in its heat affected zone. So it won't actually break in the weld. It'll break in the zone that is heat affected.
Outstanding. We're stirring non-molten bits of copper together. It's stirred. Can we look at the tool some more? I want to see what we're looking at. Like, how is it doing its thing? The tool is spinning clockwise in the machine.
Yes, really.
The cutting edges are lined up so that it almost cuts in its clockwise turning.
But at that present time, we're not cutting. So it's not like a milling tool or anything like that. We're making things molten.
But not molten.
But not molten, no.
And so friction stir welding excels when you can't have any distortion, you can't have an enormous heat affected zone. Typically it's excelling when you're using plates and sheet metals. What's the sort of range that you can friction stir weld and what sort of metals?
So I've friction stir welded all aluminium variations, magnesium, you can friction stir weld titanium, steel, copper, you can friction stir weld brass.
Wow.
Now you can't friction weld brass, but you can friction stir weld brass.
Interesting.
Because you're using a third body process. So this is called third body. So you're using a tool to do the generating the heat.
And we saw how on linear friction welding, you can effectively do an additive manufacturing process to build up pieces. The same thing applies with friction stir welding, right?
Applies, so you could just keep on adding in plates and then build up your substructure to make it actually larger.
To then save on machining costs down the line.
Machining costs, yeah.
Wow, bloomin' cool. Thank you so much. Friction stir welding gets used in tons of places that are all around you that you don't know about. Check this out. You ever been on the London Underground? Well, the new carriages are friction stir welded. High-speed rails, lots of them are friction stir welded. Rockets, friction stir welding all over them. Come see this thing. These rail cars are made out of extrusions, and the two extrusions, guess what? They're friction stir welded together. Imagine the scale of fixturing to assemble this thing. Friction stir weld, friction stir weld, friction stir weld, friction stir weld. It's all around us and I didn't even know. All right, and this is another machine. How are you, Ollie? Good to see you again. What are we looking at here? This is another friction stir welder?
Yeah, so we're looking at our large gantry milling machine that turns friction stir welder, so this can be used for both purposes.
So you can mill and friction stir weld on the same machine. So what's the plan? What are we going to see? Some 10 mil aluminium get friction stir welded?
Yeah, so this is 6082 aluminium.
Let's set it up. So the friction stir welding tool for aluminium is different than for copper. That looks different than the one that we just saw on copper.
Well, yeah, so we've got our tri-flat probe with 3 flats on, and then we've also got our scrolled shoulder, because we're welding at 0 degrees, whereas on the other machine we've got a tilt angle. Oh. So we're welding at 0 degrees straight down, and the scroll helps with the mixing of the material.
So if you can't tilt the machine so the backside of it is forging that material, you have to have a different feature in the tool.
We have a scrolled shoulder, yeah.
Very cool.
Whereas that, when we tilt, we have a concave or convex shoulder.
What's going to be different running through this 10 mil aluminium compared to the copper? Any different feeds and speeds?
Well, we can go a lot faster. I think we weld at 250 over there, and we're welding about 800 over here.
Wow.
We generate a lot more heat over there, whereas this won't get as hot.
Okay.
Copper likes to soak in a lot of the heat. We have a small ramp at the start to accelerate, and then we'll be going almost a metre a minute.
A metre a minute? You're going to be welding 10 mil aluminium a metre a minute?
Yeah.
What are you doing now?
We're in our pilot hole, 8mm deep for the probe, because otherwise your probe's doing all the work going down the hole.
crazy. Right. Oh, that is crazy. You just welded 10mm aluminium and you can touch it right after. Mate, that's absolutely crazy. Look at that. How cool is that? Brilliant. Thank you, Ollie.
That's right, you're welcome.
This stuff is bloody crazy. From 0.8mm thick all the way to 150mm thick. If you've got a big enough machine, you can friction stir weld it. Dissimilar metals too. Gets used on pressure vessels. This one's made out of titanium, to even producing near net shaped components where, by stacking up plates cut close to size and friction stir welding through that stack, you can create your final component in the friction stir welded material. I've been absolutely blown away by my visit to TWI. It is so exciting to see what gets done in the world of engineering. And our big dream is that there are some of you folks watching that are just getting so inspired and excited about the types of jobs that you could do out in the world, working in interesting places like this on fascinating projects. Thank you to the team at TWI for their incredible hospitality. Thank you to Element for sponsoring this video. Go to drinklmnt.com/forge. See you on the next one. Bye-bye.